So last week we were introduced to a hypothesis test, also known as a significance test, same thing. So now we're going to focus in on how to do a hypothesis test or a significance test for a specific population proportion. Everything we talk about today is going to be in terms of proportion. Are you good? I don't know. All right. Why? Why do we carry out a significance test? What is the point of doing a significance test? It is to see if our results are statistically significant or if they were due to sampling variability. To see if our results are statistically significant or to see if they were due to sampling variability. What does it mean for our results to be statistically significant? Our results are going to be statistically significant if our p-value is less than the significance level of alpha. If your p-value is less than alpha, then you have statistically significant results because you can reject the null hypothesis in favor of the alternative, the suspicion, the claim. The suspicion or hope. So, we get statistically significant results when we reject the hoe. Reject the null hypothesis. So we get those statistically significant results when we reject the null hypothesis. Okay? Cool? Cool. That's the reason we do a whole entire significance test. Okay, now, I'm going to tell you guys how it all works. Okay? And then I'm going to show you that your calculator is going to do the hard lifting for you. Okay? But I am going to show you how it all goes together. In Unit 8, we introduced 3 conditions that had to be met before we construct a confidence interval for population proportion. Talk about proportions here. What were the 3 conditions that we had to check to do a confidence interval for proportions? Random?
Normal.
Independent? And normal. Do you guys remember how to check the random condition?
SRS.
There's an SRS of blah, 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 right? Do you guys remember how to check the independent condition?
10%.
It's the 10% condition. 10 times the sample size has to be less than the population size. Remember, that's the one we just kind of always assume to be true, but we do still have to check it and write it down. All right, now, here's the hard one. Do you remember how to check the normal condition for proportions? There we go. Okay, we did n times p hat had to be
Greater than 10.
Greater than or equal to 10, and
N times p minus 1.
close, but yes. All right, cool. There we go. All right. We had to check that. What is that called? What?
Large count.
This is the large count condition. Okay, so we had to check the large count condition. And remember at the end, we had to write that the sampling distribution of p hat is approximately normal. We had to do all of that back in Chapter 8 when we were doing a state plan do conclude. We had to do those conditions for confidence intervals. Refreshing any memories before spring break? All right, guess what? I have good news for you. The same 3 conditions must be verified before you do a significance test for population proportion with one teeny tiny little tweak. Okay, so here's the tweak. First of all, we are still going to check random we're still going to check independent. Those have no tweaks on them. SRS, 10 times n has to be less than population. All right. Normal has a teeny tiny tweak. Okay? The normal is going to have a very small little tweak on it, and it is this. Instead of checking n times the p hat, the sample proportion, we're going to check n times p naught. That has to be greater than or equal to 10, and n times 1 minus p naught has to be greater than or equal to 10. Do you have any questions? What the heck is this p naught thing, right? All right, p naught is the claimed value from the hypotheses. So you guys know the null hypothesis that we talked about last week has this notation. It's a capital H and a little o in the subscript, right? That is not really called ho. I know, you're sad. This is actually the null hypothesis, also known as H naught. That little zero that's in the subscript is called a naught. Like, it's K-N-O-T. But it's K-N-A-U-T. There you go. H naught, that little O matches that little O. So, this is the claimed value from the hypotheses, okay? You are not going to use the sample data when you're checking the normal condition. Cool? Cool. All right, here we go. Now for the hard part. This is probably the hardest part of the whole thing. Is this page right here. All right. So I'm going to show you guys. I'm going to show you guys where the p-value comes from, and I'm going to show you guys how the distribution is created. This is probably the most important yet confusing page of notes that we're going to take today. So lock it in. Are you ready? Almost. As soon as this bell's over, we're going to be ready. All right, here we go. You guys remember our 80% free throw shooter, right? All right. Shh, 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 shh. Super focus, locked in. Are you ready? All right. If the null hypothesis is that his true proportion is 80%, if that is true, then the player's sample proportion of made free throws in an SRS of 50 shots would vary according to an approximately normal sampling distribution of p hats with the following mean and standard deviation. The mean of p hat would be equal to his claimed value if he really is an 80% free throw shooter. That is the p naught, that is the claimed value. Do you guys agree that if he really is an 80% free throw shooter, he should be at 80% for his average? Okay, that would be his average, his claimed value, okay? What would his standard deviation of his sample proportions of hit shots be? Well, you know a formula, don't you? Square root of p, it's going to be p naught this time, times 1 minus p naught divided by the sample size. Doesn't that look kind of familiar? Kind of looks like the p hat, 1 minus p hat over n from sampling distributions. We're just using the claimed value instead of the sample value. So the standard deviation of this distribution that he claims to be on is 0.8 times 0.2 over 50. 0.8 times 0.2 over 50. Square root of that. That is the standard deviation of the distribution that he claims to be on. What is the standard deviation of this distribution? What is it? Just throwing numbers out. Y'all have calculators on your desk. Get your calculators in your hand instead of your phones.
0.0566.
0.0566. Now, ladies and gentlemen, what was the proportion that he actually hit when we made him do his sample? He actually hit 0.64. Remember, it was 32 out of 50, okay? That was his particular p-hat. So here's what I can do, guys. I can find the probability that he hits 64% or less. The probability that we get a sample proportion that is less than or equal to 0.64. I can find that now. You know why I can find it? Because this is a normal distribution with a mean of 0.8 and a standard deviation of 0.0566. And I'm just trying to find the probability of being at 0.68 or less. How would I do this problem? Normal CDF. Please go to normal CDF. What is your lower boundary?
0.
Negative infinity. What is your upper boundary? His sample proportion. His sample proportion is the boundary for that area, okay? What is the mean of the distribution he claims to be on? 0.8. What is the standard deviation of the distribution he claims to be on? 0.0566. Okay, cool. Now, when you find this answer, this is the probability that he, who claims to be an 80% free throw shooter, gets a sample as extreme or more extreme than the 64%. What did you guys get? What'd you get? What'd you get? Calculators. What'd you get? .0023. Okay, now hang on. 2 seconds. Question for you. The probability that he only hits 64% or less of his free throws, if he really is a 80% free throw shooter, this number is very special. What is this number?
Alpha.
It's not alpha. It's the other one. This is the p-value. This is the p-value. This area that we are discussing right here is the p-value, the probability of being as extreme or more extreme than the sample that we observed. Now, if you remember from last week, there was a dot plot that had 400 dots on it, and there were 3 dots that were circled, and that was the probability of being 0.64 or less. And that one, the p-value was 0.0075. The reason this one is even lower is because this is an infinite amount of free throws, of a set of 53 free throws. Blah, blah, blah. This is an infinite amount of sets of 50 free throws. The one last week was just 400. This is an infinite amount. So there's even more here. So it's even more convincing that Coach Brooks is not an 80% free throw shooter, because his p-value is super low, 0.0023. Okay. Next thing is, why do we need sample data? Okay, the sample data is the boundary for the p-value area. So the sample data, that was like Coach Brooks' 0.64, That's his sample data. That is the boundary for this p-value. Okay? That's where the p-value comes from. The p-value is the probability of being as extreme or more extreme than the sample we got. P-value is probability of being as extreme or more extreme than our sample showed. That's where the p-value literally comes from. It comes from being as extreme or more extreme than what we saw when we took our sample. That is the p-value. Okay. Last thing is this thing called the test statistic. Okay? This is the last kind of big idea today, and then we'll do a state plan to conclude. Yay. The test statistic. The test statistic is a z-test statistic. The z-test statistic tells how far and in which direction our p hat is from the claimed value, which is p naught. P, our z-test statistic, tells how far and in which direction our p hat, our sample proportion, is from the claimed proportion. When someone makes a claim, that is the middle of the sampling distribution. That is the claim. That is where p naught is located. It is in the middle of the distribution. Then we tell them to take a sample, or we take a sample, or we tell them to prove what they're claiming. We get a sample. Wherever that sample is, we find how far that is in standard units. So Z tells us how far and in which direction the p hat is from the claimed value in standard units. Now, does anyone remember from back in chapter 2, what is the formula for a z-score? Value minus mean divided by standard deviation. Let's go. Well, guess what, you guys? This is going to be the value of the sample, which would be 0.64, that was our sample proportion, minus the mean of the distribution, that's the claimed value, divided by the standard deviation of the distribution that we calculated. When you do this, you will find the z-test statistic, which tells us how far and in which direction our sample is from what it's supposed to be. So when you do 0.64 minus 0.8 divided by 0.0566, what do you get?
Negative 2.83.
What that means, you guys, is that our sample was 2.83 standard units below the claimed value of 0.8. Coach Brooks hit a sample that was 2.83 standard deviations below what he should have done. Is he an 80% free throw shooter? Heck no. All right? And what's the probability that someone who shoots 80% would hit 2.83 standard deviations below? It's exactly the p-value right there, 0.0023. Make sense? So the z-test statistic is a way to know how many standard deviations are we from where we were supposed to be. Cool, cool? Cool, cool. All right, kids, I have great news for you. You don't usually have to calculate the z-test statistic or the p-value. Your calculator's going to do it for you. But you have to interpret it and write up the 4-step process. What are the 4 steps of the 4-step process? State, plan, do, conclude. Let's go. Here's how you do the state for a significance test. Are we going to estimate? No, that's for confidence intervals. What are we going to do here? We will test at alpha equals whatever. You're going to have your null hypothesis that p equals whatever the claimed value is. Your alternative is that p is somehow related to the claimed value. I don't really know which way you're going to have to go there. And then you're going to define p. P is the true proportion of blah, 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 blah. Okay? That is how you do a statement for a hypothesis test. Plan. Random, 10%, large count condition. Again, using your P naught, the claimed value in your hypotheses. By the way, this is all on this front of this green sheet, okay? On the green sheet, if it's in bold, that's what you would write down, basically, okay? All right, cool. Under do, this is where we are going to plug things into the calculator. I'll show you that when we do our example. We're going to actually be given the z-test statistic and the p-value. And then we're going to make our decision based on the p-value and the alpha. If p-value is low, what are we going to do? We're going to reject that null hypothesis. We do have convincing evidence for the alternative. If the p-value is not low, we cannot reject the null hypothesis. We fail to reject it. Does that mean we're accepting the null hypothesis? No, we just don't have enough evidence for the alternative. Okay? In our calculator, this is going to be under stat, test, and number 5. This is a 1 proportion z test. This is stat test 5. It's a 1 proportion z test. If you guys will, go ahead and go to stat test 5 so you can see it. Stat test 5, stat test 5. You will see that it looks a little different than it did back when we were doing intervals. The first thing it's asking for is P naught. What is P naught again?
The estimated.
That's the claimed value, all right? So this is the claimed value. This is going to be found in your null hypothesis. It's the number that's in your null hypothesis. This is going to be a decimal, and that is going to be fine. Now, it's asking you for x and n. Do you guys remember what x and n stand for? Okay, good.
Sampling population.
X is the number of successes in the sample. X is our number of successes in the sample. By the way, this is the first time that you will use the sample data in your problem, is right here. You don't use it until you get here. N is your sample size, just like it always has been. And then, if you look at your calculator, it looks very different than what you have seen before. It says your proportion. Is it not equal to the claimed value? Is it less than the claimed value? Or is it greater than the claimed value? Basically, you have to pick which one of these matches your alternative hypothesis. Okay, so this should match the alternative hypothesis sign. Once you hit calculate, you'll have two options. You'll have calculate, and that'll give you your test statistic, your p-value, and all the things. Or you can do draw, and you can actually see the normal distribution with the p-value area shaded. We will go through and look at both of those on our example. Cool? You ready to do an example? Sure, why not? Let's do it. California is what our example is about. We are going to do a one-sided test. Does anyone have any thoughts on what that might be? A one-sided test. There's not two sides. So what might be going on here?
Bias.
No. Y'all are funny. That's your answer, right? It's like that's your Jesus answer. What do you think? One-sided test.
Only tested one.
Close. We're only looking for evidence from one side of the claim. Here's what I mean. Your alternative sign will be a less than or a greater than. It will not be a not equal to. It will not be a not equal to. One-sided test means that I can only get evidence from one side of the claimed value. Okay? For example, if Coach Brooks says he's an 80% free throw shooter, and I say, no, you're not that good, you are less than an 80% free throw shooter, that means I'm looking for him to show me that he's less than 80%, right? If he goes and shoots 90%, does that help me any? No. This is a one-sided test, meaning I'm only going to look for evidence on one side, okay? All right, California. A recent report states that 55% of U.S. adults use Netflix to stream shows or movies. An advertising company believes the proportion of California residents who use Netflix is greater than the national proportion because Netflix headquarters is located in Los Gatos, California. The company selects a random sample of 600 adults from California and finds that 360 of them use Netflix. Is there convincing evidence at a 5% significance level that more than 55% of California residents use Netflix? State!
We will test at a significance level of...
We will test at alpha equals 0.05. By the way, why do I know that alpha is 0.05?
5%.
It said so in the problem. What if it doesn't give you a significance level in the problem? That's your go-to. 0.05 is the standard. 5% is our standard. If you don't have any other significance level given, go with 0.05. All right, cool. Null hypothesis. What's the null hypothesis? Y'all should be really good at this now.
P equals 0.5.
P equals 0.55. What's the alternative hypothesis? P is greater than 0.55. And what does P equal?
360 over 600.
Nope, that's P hat, but that's the true proportion of what?
Of California residents.
California or U.S.?
California.
California, because we're talking about California. Very good. True proportion of California residents who watch Netflix. Cool. That is how you do the state part for a significance test. Do you guys have any questions on that? That's pretty easy, right? All right, what's next? Plan. Let's plan. Random. Do we have a random sample?
Yes.
We have an SRS of 600 California residents. All righty. Independent. I need to make sure that 10 times the sample size is less than the population. So 10 times 600, that is 6,000. Do you think that the population of California is more than 6,000?
Yes.
I mean, maybe slightly. Just slightly. Random, independent, yes, sir. Anything else that we need to do for plan? Oh, we need to check the normal condition. All right, I'm going to go ahead and erase this because I need to do the normal condition. All right, kids, normal. Now, for normal, we need to check n times p naught is greater than or equal to 10, and n times 1 minus p naught is greater than or equal to 10, all right? So we're going to use the claimed value of the population, the 0.55, for our p naught. So 600 is our sample size, 0.55. What is 55% of 600?
30-something.
330.
Oh, yeah.
Is that greater than or equal to 10? Most days. And then 600 times 0.45 is 270. And that is also greater than or equal to 10. Does anyone need me to explain where the 0.45 came from?
Yeah.
0.45 came from 55 is our P naught. 0.45 is the complement of that. So 0.55, 0.45, those add up to 1. And am I done with normal? Say yes, and I'll come over and smack you.
The sentence.
What do you have to say?
Sampling distribution is approximately.
Sampling distribution of P hat is approximately normal. Boom. Life is good. All right. Now what can we do? We're going to use a 1 proportion Z test. 1 proportion Z test. We are not doing intervals anymore, children. At least not for today. We are going to use a 1 proportion Z test. Cool? All right, here we go. Everybody go to stat test 5. You should already be there, I guess. What is your P naught? What are you putting in from the hypothesis statements? 0.55. And now, for the first time, we're going to use the sample data. What is the number of successes in the sample? AKA, what is the number of California residents that use Netflix in the sample? 360? Sample size? 600. Because it said in the problem that 360 of our sample. Now, we need our proportion to be the greater than P naught selection. Make sure you go to that one. Now, this first time, you guys, I want you to do me a favor and hit calculate. I know you want to see the other one, but go ahead and hit calculate first. X is the number in the sample, in the actual sample. That's a great question that Part just said. Part said, hey, don't we normally use the 330 like before? Yes, we did before, because before this was the P hat. But now this is not the P hat. This is the actual sample that we're putting in down here, okay? All right, guys. Hit calculate. Do calculate this time. I promise you I'll let you see draw in a second. What is your Z test statistic? 2.46, is that right? Okay. Now, the very next line, you guys, is very misleading. It says P, but it is not the true proportion. That is the P value. That is your P value. You need to make sure that you write the word P value. Don't put P. Your calculator just doesn't say P value, but that's P value. What is your P value? 0.007. Okay. Then it gives you your P hat in case you wanted to know what it was. That would be whatever 360 over 600 is. What is that P hat value? 0.6. Okay, now, here's what I want you guys to do. Go back to Stat Test 5. Don't change anything, but go to draw for me. Go back to Stat Test 5, but this time please select draw. I want to explain to you guys what you're seeing here. The mean of this distribution is supposed to be 0.55. We got a sample that was at 0.6. That was our p-hat. And that is 2.46 standard units from where it should have been. And the p-value, the probability of being as extreme or more extreme than that, is 0.007. That's the whole picture and how all these things come together. Questions about that? So, what do? We conclude now. How are we going to conclude?
The p-value equals blank.
Perfect.
Which is
Yep. P-value, this is
less
conclude.
than the alpha
Conclude. P-value,
equals 0.007,
0.007. Now, how does that relate to the significance level for this?
which is less than alpha.
That is less than the alpha of 0.05. And what do we do when the p-value is low?
Reject that.
We are going to reject that hoe. We're going to reject that null hypothesis. Guys, why did we reject the null hypothesis?
There's convincing
We have convincing evidence
with the alternate, the whatever.
that the true proportion of California residents who Netflix is greater than 0.55. And that is how you state, plan, do, conclude with a hypothesis test.